star RS Puppis. And if you want to know about it, well, simply flip over. We have a description of it along with pointers for where you can get even more information about it. Grab those on your way out. Tonight, we have how to find an inhabited exoplanet. A purposely intriguing title, which I know is going to also be an intriguing talk tonight. Next month, a view from mission operations. A lot of things that go on in the background behind all of the science results that we present, how we actually operate the missions. Courtney McManus has agreed to give a talk about this very important topic. In September, Nolan Walborn, he's spoken here a few times, will be talking about active luminous blue variables in the Large Magellanic Cloud. That's a mouthful, right? That there are variable stars, there are blue stars, there are luminous blue variables, and they are even active. And they actually tell you an awful lot. Nolan promises that he will challenge you, okay? So bring your thinking caps in September when Nolan speaks. And in October, one you won't want to miss, bring the kids, Cassini's grand finale at Saturn. Cassini has been orbiting Saturn for over a decade. I forget when it got there. Do you remember when it got to it's like 2006 or something? So it is just amazing what Cassini has found at Saturn. Its grand finale is in September, and our own Bonnie Meinke from the Office of Public Outreach, who specializes in Saturn, will be giving the talk to tell you how it executed its grand finale. She'd have to have a talk that's 6 hours long to cover everything that Cassini has done, but she'll cram as much as she can into a 1-hour talk. The details are on our website. Just use your favorite search engine for Hubble Public Talks, and you should find this page with a list of our upcoming lectures. And you can watch live online. This is the link to our webcasting. Also, you can watch past lectures all the way back to 2005, 12 years of astronomical goodness for you to explore. You can also sign up for our email list here, and a lot of you have taken advantage of that. So I'm glad that there are a lot of people getting informed about our lectures. The announcements, sign up at the website. If you want other ways of getting it to you, you can. For those of you here in the audience, you want to walk down and write your email address and hand it to me, I'll make sure you get on the list. If you want to contact us and ask us comments or give us questions, public lecture at stsci.edu. Of course, we have the usual social media. I will have to update this page at the end of this month because that woman right there has got a whole new suite of social media pushes that we're doing this month, and she'll update me and make sure I have that. So next month this slide will be updated, but we have the usual Facebook and Twitter and Google Plus and Pinterest and a few more that she's going to tell me about this month. I have my blog and Facebook and Google Plus and Twitter that I use every now and then, but I'm usually too enthused with my work to spend much time on social media, so don't expect a lot from me. Observatory tonight. Yes, it will be here. Weather permitting, it looked like it was clear when I came in, so I hope it will still be clear. Irini Lambrides will be here. I'll have her come down front, and you guys can go with her and go across the street. You cannot be a laggard on this. When Irini takes a group across, if you're not with the group, you don't get in. The doors are locked, so the whole group has to go in as one. So unfortunately, so that means sometimes you can't hang around and ask the speaker questions if you want to go do the observing across the street. All right. And now my section, News from the Universe for July 2017. First story. The curious instant of the star in the nighttime. Now, who recognizes what that's a reference to? Anne does. I know she does. Who is it?
The autistic child curious incident of the dog in the nighttime.
Yes, it's from, it's actually from Sherlock Holmes, is where I took it from, where Detective Gregory asks Sherlock Holmes, "Is there any other point to which you would wish to draw my attention?" And he replies, "To the curious incident of the dog in the nighttime." The dog did nothing in the nighttime. That was the curious incident. Now, it's come down through folklore as the dog that didn't bark. Here we're going to talk about a star in the nighttime, and stars do other things besides barking. So this is a picture in 1984 of a certain particular star taken at the Anglo-Australian Observatory. And that star in 1987 looked like this. This was supernova 1987A. And so very massive stars at the end of their lifetime explode as these giant supernova explosions. And they become incredibly bright, basically as bright as an entire galaxy. Okay? So that's how we expect these very massive supergiant stars to end their life. Let me tell you a story of a different star. This one. Now, there is a supernova search that's being run out of the Ohio State University, and they're using a ground-based telescope, the Large Binocular Telescope, and in order to find supernovae, because you don't know which star is going to go supernova at any time, you monitor lots of galaxies over many years. And on average, you'll see a few supernovae in each galaxy, in some of the galaxies that you're monitoring. Well, this star right here turns out to be a 25 solar mass star. It's in the galaxy, what is it, NGC 6946. And this star was observed to brighten in the year 2009, but since then, it has faded away. Now, when I say it brightened in 2009, it didn't go supernova. You saw that huge brightness change there. It did not brighten enough to say it went supernova. It brightened a bit, but it did not brighten to a huge amount. And then it faded away such that the ground-based telescopes could not see it. Well, they wondered what was going on. Was this star just enshrouded in dust and we couldn't see it? Or maybe it had faded away to such it was undetectable by ground-based. So what do? You call in the space telescopes for follow-up, all right? This is what Hubble saw. Nothing. It was not that the star had just faded below observable level from the ground. Then they looked with the Spitzer Space Telescope. Perhaps it was shrouded in dust and therefore obscured in optical bandpass, but that would be visible in the infrared bandpass of Spitzer. Spitzer also saw nothing. It's not visible in optical light. It's not visible in infrared light. What happened to this 25 solar mass star? Well, the conclusion is this is not the dog that didn't bark. This is the star that didn't explode. This star, they believe, collapsed to a black hole without going through a supernova. Normally, we believe that stars, that at the end of the star's life, it collapses, it explodes, and the core collapses to either a neutron star or a black hole. This is evidence that stars may collapse directly to a black hole without going through the supernova phase. This had not been seen before. This is the first one of what they call failed supernovas. And in their survey, they saw 6 or 7 other supernovae in the galaxies they were monitoring. And that starts to give them some statistics about how many of these very massive stars might collapse directly to black holes without leaving the telltale explosion of a supernova. So this is a new way for forming a black hole. We believe that you can form black holes from the standard model where you have an explosion and you get the supernova explosion and you get the black hole. But here we have evidence that you can get a black hole without having a supernova explosion. That's really cool. Now, third story, a stellar light weight. So if you want to weigh a star, you want to understand the mass of a star, you have to figure out how much gravity that star has. And the usual way to do it is if you've got a planet or another star orbiting around it, the characteristics of that orbit will tell you the amount of gravity that is in the system and therefore the mass of the star. This is a dynamical measurement of the mass of a star. But if a star is isolated, doesn't have anything orbiting around it, how do you tell its mass? Generally, you can't, except the mass of a star can also do something else. In Einstein's relativity, we think of the fabric of space-time, okay? And let's represent it here as this grid. But the presence of a star creates a deformation in the grid of space-time. light that passes through that deformation changes direction. So, and the amount of directional change is going to be proportional to the mass of that star. So if you can measure that, you can measure the mass of the star. And this is what Hubble is trying to do for this star, Stein 2051b. And actually, I just lied to you. It's not a star. It's a white dwarf. Now, you'll always hear it being called a white dwarf star, but a white dwarf isn't a star because there's no nuclear fusion going on in its core. It's a dead star. It's a stellar remnant. All the nuclear fusion has ceased. It's just a really, really hot ball, basically of carbon. Now, you can sort of think of it as a giant charcoal briquette that will burn for trillions of years. You can have a really, really long barbecue with this. So Stein 2051b, you might think that it has a planet around it or another star nearby it, but it doesn't. This is actually passing in front of a star that's 5,000 light years away, whereas Stein 2051b is only 17 light years away. So Stein 2051b being very close and this other star being very far away, they move relative to one another in the sky, and as Stein 2051b passes by that star, we should be able to measure the gravitational lensing of the background star. So here's the diagram. This is the white dwarf, okay? Here is Hubble's observed star position, and here's where the star position really should be. And if we can measure that deflection, we can then measure the mass of the star. Here is a diagrammatic. This is an illustration of the idea that as the white dwarf passes by, the position of that star will change, okay? Now that's incredibly overstated, all right? That's an illustration of it just to give you the idea of it. Do you want to see the real data? I'm happy to show you the real data. This is the real data. Did y'all see that motion? Of course you didn't, okay? Because the motion of that background star is offset by 2 milliarc seconds. 2,000ths of an arc second, where an arc second is 1/60th of an arc minute, and an arc minute is 1/60th of a degree, okay? So 1/3600th of a degree, and then 2 1,000th of that. That's a really small angle, but Hubble was able to measure it. And using this, Hubble was able to measure the mass of the white dwarf star, the result being about 2/3 of the mass of the sun, which fits in with our theoretical expectations for the masses of white dwarfs. And actually, it fits in with our other observations of the masses of white dwarfs. This actually is the second star for which it had been done. When was it done the first time? 100 years ago, during the 1919 total solar eclipse. Just after general relativity was put forth in the paper, they recognized that they could see this gravitational lensing of background stars during a solar eclipse. So what they did is they measured, you see all those stars I've got pointed out there? They measured those stars well before the eclipse, where their positions were, and then when the sun underwent the total solar eclipse and the moon was blocking it, they could actually see those stars passing through the gravitational field of the sun. They could measure the deflection of light to test general relativity, and they did this in 1919. So Hubble is finally doing for external stars what was done for our own star in 1919, and we have a new way to measure stellar masses, which also gives us a good entry into reminding you, hey, where will you be when the light goes out? Just want to make sure you all remember that next month, on August 21st, 2017, we have the greatest total solar eclipse so far in my lifetime in the United States. It passes from Oregon all the way down through South Carolina. All right, it is about 2 minutes to 2 minutes and 40 seconds duration if you're on the center line. It's on a Monday. Make sure that there are all sorts of things. If you can't get to the center line, you can see that the entire continental United States will have some level of the partial solar eclipse. There are all sorts of cool tools online. For example, this one is an interactive map, and if you click on Salem, you find that Salem is in the path of totality. It will have a 1 minute and 55-second totality. However, if you don't leave here, if you stay at the Johns Hopkins University campus in Baltimore, Maryland, you will only get an 80% obscuration. And here are the times of the eclipse. You can find all these incredible tools online. We gave a talk on this in January. If you go to our webcasting site and go back to our January one, you can find our talk on that. Although I'm sure there's a lot more cool stuff on the web now because everyone's hyping up for this. I will only say one thing. You must have certified solar viewing glasses. I cannot say this enough, okay? Sunglasses are not good enough. Okay, a Mylar balloon, which some people think is good enough, is not good enough. What your Uncle Joe from Montana tells you is good enough isn't good enough unless he says you need certified solar viewing glasses, okay? So please make sure that if you're going to watch the solar eclipse, you keep your eyes safe. All right, and that's our news for July. You have a question here?
Sure. The mass of the sun when it was measured back in 1919, how does that compare in accuracy to other measurements that we've made since then?
Well, in 1919, the main, all right, so the question, I got to repeat it for the online audience. The mass of the sun measured in 1919, how does it compare to the mass we would measure today? And the main point of the eclipse expeditions in 1919 was actually to test whether those stars actually really moved, whether general relativity was correct. Because this was a mathematical theory that, stretched the imagination a bit. And so the main point of it, so I don't really know whether they measured the mass of the sun but I think they probably put in the mass of the sun as one of their parameters to measure how much the stars should move in the light deflection equation. We have, obviously, planets orbiting the sun, so we can measure the mass of the sun pretty accurately using that. I don't know if that light deflection actually would improve on that in any way. But, yeah, it's a good question. Thank you.
Frank, I have a question.
Yes.
Your first story about the star that was 25 solar masses, is that rare for a star to be that big, or
So, in the story of the star that didn't explode, is it unusual to have a 25 solar mass star? Yes. Okay. The meek inherit the universe. The tiny, very small stars, smaller than the sun, are the most numerous in the entire universe. The red dwarf stars are really the most numerous. As you get up to larger and larger stars, they're much rarer. And so a 25 solar mass star is a relatively rare star. As a matter of fact, the stars you have to get above at least 8 solar masses to have supernova, and those are the O and the B stars. So those are the few and far between. Those are the big monster stars inside the star clusters. All right. Okay, let's move on to our featured speaker. I am extremely pleased to have Dave Charbonneau of Harvard University here tonight. He is a professor of astronomy. He's a professor of astronomy at Harvard University, and his research, as you might guess, is on exoplanets, and you'll hear a lot of his stuff here tonight. He has worked on both the Kepler mission, and he's working on the upcoming TESS mission, the Transiting Exosolar Survey Satellite, Exoplanet Survey Satellite. There we go. I usually say extrasolar planet when I'm talking to the public. Instead of exoplanet, yes, you went to exoplanet. All right. Let's see. He did his undergraduate work at the University of Toronto postdoc postdoc at Caltech, so he's hitting all of the high points of the universities. He has, the usual awards like the Waterman Award from the NSF, the NASA Medal for Exceptional Scientific Achievement, Scientist of the Year from Discovery Magazine. He's a member of the National Academy of Sciences, yada, 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 the usual stuff that we have. I only get you the best speakers, okay? But most important thing is he's the father of 4 girls. He is a hockey coach, and he tells me he's probably the only male to be a Girl Scout leader, or at least in his area. He's one of the few rare males to be a Girl Scout leader, so a definite Renaissance guy. Ladies and gentlemen, please welcome Dave Charbonneau.
Well, thanks for the really kind introduction. So I'm really looking forward to this. What I want to do is just tell you about what I think is the most exciting thing going on in all of science. Maybe I'm a little biased, but this is a very, very special moment to be alive and be interested in this question of whether or not we're the only inhabited planet out there, okay? So, I'm sure you are all aware that if you take a telescope out to a dark point on the Earth and you point it up at the night sky and you just take a long exposure, it's stars all the way down, right? So it's not just the stars that you see in the image, but the fact that there's all these kind of unresolved stars mean that if we add them all up, there's something like 300 billion stars in the galaxy, okay? And often when I'm talking to folks about whether or not we're alone, they say, look, we now know that there's planets around other stars. There's 300 billion stars out there in our own galaxy. There's hundreds of billions of other galaxies. Isn't it inevitable that there's life? And I find that answer to be awful. I find that to be really unsatisfying. I don't want to know that there's a mathematical possibility that there's probably life. I want to actually find the life, and I want to see if it's got DNA, and I want to see if it's multicellular, maybe even if it's intelligent, okay? So it's not enough to do the calculation. We have to actually go, I think, and actually look for it. What I do want to point out is that this is not a new idea, okay? We're not the first generation to really worry about these things. If you go back through at least more than 2,000 years of human written thought, you can find that people have been thinking about whether or not we're alone for a long time. Okay, so here we have Epicurus, okay, writing in 300 BC. There is an infinite number of worlds, some like this world and others unlike it. Some of these worlds contain the seeds out of which animals and plants arise, and all the rest of the things that we see. So the Greeks didn't even really know that the points of light in the night sky were stars, and there might be planets around those stars. But even without that knowledge, they had this thought that there might be alien worlds, and we would somehow come into contact with these unknown places, okay? Here, much more modern, only, 450 years ago, we've got Giordano Bruno. So he was a medieval scholar, and he said there are countless suns and countless Earths all rotating around their suns in exactly the same way as the planets of our system. The countless worlds are no worse and no less inhabited than our Earth. So he now knew that the points of light in the night sky really were stars. He didn't know that there were planets, but he thought, well, they're probably planets. We just can't see them. And he thought, well, maybe some of them have life. What's so special is that for thousands of years, people have only been able to theorize. They've been able to use their imaginations and say, gee, I wonder. But we're all alive at this special moment in human history where we have the technological ability to actually go and answer that question. Okay? So this is a very, very special time. How are we going to do it? Right? How are we going to do it? How are we actually going to find out? I mean, there's only one generation that gets to do it. You only find out you're not alone once, right? So here's kind of one idea. Maybe we should build spaceships, right? And often when I'm talking to folks, they say, is that a possibility And you know, I want to point out that, of course, that's not really a realistic possibility for discovering life on other planets. There are people thinking about what it would take to send probes to other stars, and that's very, very exciting. But it's not the way the first discoveries are going to be made, and it's a really difficult challenge, okay? So if you take the fastest spacecraft that we've ever made, and you pointed it directly at the closest star, and you fired the engines, you're still talking something like 10,000 years to get there, okay? So I am impatient. I've got things that I've got to go coach my hockey team, so I can't wait that long. So here's another idea. Right? The search for extraterrestrial intelligence. So we should listen for radio signals or for laser signals from intelligent life that's trying to communicate with us. Now, I am really glad that people are trying to do this, but I don't think it's the way to make the first discovery. And the reason is it has a lot of assumptions, right? It's not enough that there's life out there. The life has to be interested in technology, it has to be interested in radio telescopes or lasers, and it has to want to communicate. Okay, maybe that's just, unfortunately, a human desire. So the more I really think about SETI, I think, well, we're really kind of looking for ourselves. Now, I'd hate to miss it, and gosh, if they find something, I'll be the first to, you know, celebrate it. But it's those additional assumptions that make me a little bit nervous. And so what we're trying to do as astronomers is we're trying to come up with a much broader net, a very robust idea that's going to go and find life, even if the life is not interested in actually being found. Okay? All right, so what's that idea? Well, to put it in perspective, the difficulty is, of course, we first have to find the likely places for life, and we think those are planets, all right? So just to remind you how hard it is to find planets, it's only about 20 years ago that we found the first planet orbiting another star, sun-like star. And to put that in perspective, let me show you the Earth, okay? Everything you know and love, all the history of humans and all of our wonderful art and theater and thought throughout generations, it's all that blue marble. And of course, if you put it in perspective next to even another planet in the solar system, it looks kind of small, right? There's Jupiter. And of course, if I keep the scale, everything here is drawn to scale, and I now put the sun up on here, okay, then you can see that the Earth really doesn't amount to very much. So very, very precious for us, but really not a big player in the solar system. So that's why progress was so slow. Progress was slow because planets are small and they don't put out much light. So compared to the stars they orbit, they're simply overwhelmed and we don't see them. So how are we going to find those planets? Well, I showed you the answer right away. Did you see it? Did you see it? Yeah. So of course, at the end of the title I hope you weren't, that's not a period. Okay. That's an actual image. That's a real image. This is not something I did in Photoshop. That's a real image. Taken in 2012, when, of course, Venus went in front of the sun. And did anybody here see that? Yes? Did anybody decide that you needed a 2-week family vacation in Hawaii to see the whole thing? Yes? Yes, you did? Okay, good. So that's Venus going in front of the sun. And that's how we're going to find these planets, that idea of a transit. So the idea is the planets are going to go in front of their stars. They're going to make their presence known because they're going to block some of the light from the star. So all of a sudden the star goes from being an adversary, this really bright thing blocking our view of a faint thing, to an ally. The star's light is now what's going to betray the presence of those planets. Now, if we zoom in on the planet and we look very carefully, we see something very, very intriguing. And Tom, I don't know if it's possible just to bring the lights down a little bit for this one slide, please. Okay, so in the 1760s, a Russian scientist by the name of Lomonosov was observing a transit of Venus. These are very rare. He was observing a transit of Venus, and he noticed this is Venus now, okay? The sun is enormous at the scale. The sun would go down several stories, right? So we're just zoomed in on the planet. And what he noticed was that the part of Venus that wasn't yet in front of the sun was still illuminated. You see? There's that light arc. And he said, oh, Oh, I bet you that's refraction. That's the bending of light. And so if light is bending, there must be an atmosphere. And so he deduced that Venus had an atmosphere, that other planets had atmospheres. It wasn't just a property of the Earth. And he was right. It's an amazing induction that he made from a very large distance, never actually going to the planet directly. Using this geometry, he was able to infer that planets had atmospheres. That is how we're going to make progress. Okay. So, so here are really kind of the goals that I want to tackle today. Really, I want to do three things. I want to describe the methods by which we find and characterize these planets, and I think I've already kind of played my hand here, which is it's going to be through transits. I want to describe our current state of knowledge of Earth-like exoplanets. Okay, so what do we actually know about planets that are similar to the Earth? And then I really want to describe a kind of a first opportunity for going and detecting life. Okay, so there's many, many ideas. Astronomers, actually I'm here because there's a conference right now going on about how we might use a future great observatory, which I'm going to tell you about. So astronomers are thinking hard about this issue, and this is my thoughts on how we're actually, our first opportunity. It might not work, but it's the first time we have a genuine shot at this thing. Okay, so just to remind you how we actually do go and find those planets, there's of course the Doppler wobble. So the idea is the star is not fixed, but the planet and the star do-si-do around each other. Sort of picture them as like two dance partners, but one dance partner weighs like, 300,000 times more than another dance partner, okay? But if you looked at the big dance partner, you would still see that they were kind of, wobbling around, and you'd infer there was another body there. So that's the Doppler method. That's important because that gives us the planet's mass. Then the transit method, I've already described that. That's the idea where the planet goes in front of its star, and the fraction of light that it blocks, if it blocks a lot of light, it must be a big planet. If it doesn't block very much light, it must be a small planet. And so if you can put these ideas together, if you have a planet and you can measure its mass, and you can measure its size, then you can calculate a density. And so without ever having been to the planet, we can figure out, is it a rocky planet or is it a gas giant planet? We don't think gas giant planets are going to be good places for life. We think we have to find rocky planets with a thin ocean. So we're looking for rocky planets. The other exciting thing about transits is that they allow us to go after the atmosphere. Okay? So as the planet passes in front of the star, some of the light from the star is going to pass through this little onion skin and imprinted on that starlight, which then travels through space and we capture it with our telescopes. Imprinted on that starlight is the chemical fingerprint of whatever atoms or molecules are present in the atmosphere. Okay? So we're never going to see these planets. We're not going to take a picture of them. There's not going to be any photographs, but we can figure out their size, we can figure out their mass, we can figure out what their composition is by their density. We can even study what their atmospheres are made of. All by kind of clever thinking about how to make the star an ally. And this field has really taken off. Okay, so in 2001, there was one such planet. There was one such planet, and we just figured out how to study its atmosphere. In 2017, there are more than 5,000 such worlds, and we've studied the atmospheres for a little over probably 100 of them. I've thought about many ways to try to express the following idea, and here I really have to give credit to Zach Berta-Thompson, who's a professor at the University of Colorado, who I see has joined us. Zach was also my student at Harvard. He captured it in a nutshell through an image. The idea is that there's something really special about the Earth, right? If you were an alien looking at all the planets of the solar system, you would see that there's something really different about the Earth. The Earth has been transformed by biological activity. The continents are green, right? They should be brown if it's just rock, okay, like Mars. But they're green. And sometimes they change color because the vegetation grows and disappears in the fall and comes back in the spring. And importantly, the air on that planet is full of oxygen. Now, you would know that oxygen likes to react with things. There shouldn't be a lot of oxygen. But yet, here's this planet with 21% oxygen in its atmosphere, driven by biological activity. So that's the idea. It's not radio signals, it's not spaceships. It's that the inevitable chemistry of life, the waste products of life really, change the appearance of a planet. Life has radically transformed the way the Earth looks and the way it smells and the things in its atmosphere. And those are the things that we look for remotely with our powerful telescopes, whether or not life has any interest in communicating. Okay, so now connect that idea to the possible. There's the ideas of what's out there, and then there's what can I do? This is the opportunity, the James Webb Space Telescope. Okay, so here we are, at the place where I'm here for this 2.5-day meeting, talking about how to use James Webb to study planets. And here we are, only about a year away from launch. James Webb is the successor, both in terms of hardware and in terms of ideas, from the Hubble Space Telescope and the Spitzer Space Telescope. But of course, it's an enormously, a much larger and much more powerful observatory. As many of you probably know, it's a local kid, okay? It was assembled at the Goddard Space Flight Center, and some of you maybe even got a chance to actually see it being assembled. And it is enormous, okay? It's 6.5 meters in size, okay? These are normal-sized humans here working on the telescope, okay? And these are the individual mirrors, some of which have covers on them, and some of them which don't, and they have that kind of gold look. If you didn't get a chance to see James Webb, I'm sad to say it's gone now. It's moved to Texas. And the reason is that there's a whole bunch of testing that you have to go through before you get to go to space. Okay? And so now it's gone to Texas to use this enormous cryogenic testing chamber. And they're going to put the James Webb Space Telescope in there, cool it down over many months, I believe, and do various tests and make sure that everything performs exactly as it should, so that when it's out in the coldness of space, there are no surprises. James Webb will be so far from the Earth, there is no chance to go and service it the way we did with the Hubble Space Telescope. It is farther from the Earth, it will be farther from the Earth than any human has ever been. Right? The farthest people have been is the moon. You might worry, by the way, is it going to fit? And I want to point out it does barely fit, okay? But of course, NASA's very good with precision. So they knew going down there it was going to be a tight fit, but a possible one. Okay, so the idea is James Webb, very special opportunity, much more powerful telescope, very good infrared telescope, much bigger than anything that's been put out in space. Maybe it can do something for exoplanet atmospheres. I want to introduce another telescope that you might not be so familiar with, which is the Giant Magellan Telescope. Giant Magellan Telescope is enormous, okay? It, at the time that it is constructed, we think it's going to be finished around 2023. It's going to be the largest optical telescope ever built, but it's on the ground, okay? James Webb is 6.5 meters. That's the biggest thing we know how to get up into space right now. It's obviously very expensive, very heavy to get things up into space. This is a much bigger telescope, but it's going to be located in Chile, okay? So it has to look up through the Earth's atmosphere to make these measurements. Just to make sure that you all understand how truly enormous this telescope is, it's composed of 1, 2, 3, 4, 5, 6, 7 giant mirrors. Each one of these mirrors is about 25 feet in diameter. So the James Webb Space Telescope, its entire mirror is smaller than one of these mirrors, okay? So there's a person, remember we had people dangling down before? Okay, look how big a person is now compared to this entire thing. In fact, if you take this middle mirror, which has got a hole in it, because when it's all assembled, that's where the light goes through to be studied. If you take that middle mirror, there it is. It's not polished yet, but all these people are sitting on the mirror blank, okay, before we go through the actual polishing, which is all being done in Arizona. So we've got the James Webb Space Telescope, which is undergoing testing, ready to launch in 2018, going to be up in space. Giant Magellan Telescope, we are still figuring out how to pay for it, but we started construction. That's a real challenge. It is not a federally funded project, okay? It is a very interesting collaboration of US partners and the national science foundations of many other countries. But it's not fully funded. That is the main challenge with the GMT. But confident that we'll get this thing together in 2023. So if I put these together, right, we've got these two really unprecedented observatories, the Giant Magellan Telescope and the James Webb Space Telescope. They will have the power to access the atmospheres, perhaps, of Earth-like planets. So what is the challenge, given that these telescopes are getting built? Okay, the challenge is we don't yet know where to point them. So it may sound shocking, but we actually haven't found the planets orbiting the very closest stars to us, right? So we actually have found a lot of planets that are at somewhat larger distances out in the galaxy, but we haven't actually figured out which of the very closest stars, which are the most accessible to telescopes, actually have the planets that we seek. So how do we remedy that? Okay, so again, to remind you of the challenge, here is a picture of the sun. Okay, and can anybody see the Earth-like planet in front of the sun? Dropped one in there just to mimic it. Okay, it's not, these are star spots. They're bigger than the Earth, often. But it's right over here. Okay? So that's roughly how big the Earth would look going in front of a sun-like star, viewed from the distance of another star. So that's really, really hard to discover. That's really, really hard to find such a small thing going in front of such a big thing. NASA knew how to tackle that. That was the Kepler mission, right? I hope you've all heard of the Kepler mission. The Kepler mission launched in 2009, operated for 4 years. It's now still operating, but in a different way because of a hardware failure that prevented it from gathering data the way it had been gathering data for 4 years, and that's called the K2 mission, which I won't focus on here. But during these 4 years, it studied 150,000 stars, and the purpose was to figure out how common planets were around stars in general. So with 150,000 stars, it could actually do statistics. Okay? Now, it found all sorts of different kinds of planets. It found small planets, big planets, wild architectures. There are planetary systems where you have a gas giant and a rocky planet, and then a gas giant, and then a rocky planet, and then a gas giant, completely unlike the solar system where things are nicely divided. But there's one result in particular that I want to focus on. Of course, what I'm interested in, if we want to answer this question of whether or not we're alone, is how common are Earth-like planets? So to be Earth-like, you have to be rocky, you have to be sort of Earth-sized, and you also have to be the right temperature, right? So if I take a rocky planet and I put it too close to a star, then the water will boil, and it'll be gaseous. If I move it too far from the star, it's good for hockey, but bad for life, which is it's all frozen. So you have to be in kind of this Goldilocks zone. So of all the 150,000 stars that Kepler studied, most of the time we didn't see planets because they just didn't happen to be lying along our line of sight, but there was still enough that we could do statistics. And I really am delighted to say that we now know how common Earth-like planets are in the galaxy. We actually know how common is it that the typical star in the galaxy has a planet that's the same size and the same temperature as the Earth. And what I'm particularly proud of is that result, so there was an enormous amount of work that went into the Kepler mission, okay? It was hundreds of scientists and engineers. They produced this data. The data was used for many different studies. But the particular question of the statistics of Earth-like planets, that was figured out by Courtney Dressing. Courtney was a graduate student working with me at Harvard, and she was the first person to ever know how common they were. So it could have been 1 in a million. It could have been the Star Trek universe, where every star has an Earth-like planet. Courtney found out the answer is 1 in 4. Okay? So 1 in 4 stars has an Earth-like planet, which is fantastic news if you want to go and follow them up. Because if it had been 1 in a million, let's say 1 in a million stars had such a planet, then that would mean the closest one to us would still be so far away that it would be beyond our ability to study it with things like the James Webb Space Telescope and the Giant Magellan Telescope. But this now gives us hope. This means that even the closest stars might perhaps have such a planet. So how do we actually go and find the planet we want to study? Well, we can't use the ones that Kepler found. Kepler was looking at 150,000 stars, but the stars were all quite far away. If we want to study the atmosphere of a planet, we need the star to have two features. First, the star has to be very, very close by. Okay? If the star is close to us, obviously it's a lot brighter. We get a lot more information from it more quickly. And we also care about how big the star is compared to the planet. If I can shrink the star, then the planet's atmosphere blocks proportionately more light. Okay, the atmosphere doesn't change. I'm not changing the size of the Earth. But if I can shrink the star, then relative to the star, the atmosphere starts to look very big, and it makes my measurement easier. So it's a very opportunistic thing, okay? I simply want to find close-by stars, and I want them to be as small as I can make them. And that gives me the best chance for going and studying the atmospheres of those planets. As it turns out, I was told a big lie in high school by my science teacher. Did any of you get the same? I was told the sun was an average star. Heard this all the time in high school. Sun is an average star. Big lie. The sun is not an average star. The sun is much, much bigger and more massive and puts out a lot more light than the typical star. The typical star is what we call a red dwarf star. It's about 1/4 the size of the sun. It's about 1/4 the mass of the sun. And it puts out about 1/1000th the amount of light. Okay, so if the sun is like a big 1,000-watt light bulb, this is a little Christmas tree light. Okay, but that's the dominant mode of star formation in the galaxy. Sun-like stars are actually quite rare. Great news, right? Great news if you want to go and find Earth-like planets, because I just told you I want to make the star small. That also has the benefit of shrinking the habitable zone. So the idea is, you want to find the distance around the star at which your planet is going to have the right temperature. If the star is very, very bright, you have to move far away. But if the star puts out very little light, then the planets want to kind of huddle in close to just have the right temperature once again. The benefit of that is if they're in close, they go around much more frequently. So instead of having to wait for a signal that I see once a year, right? If an alien was studying us, they would only get to see us go in front of the sun once a year. Now they might go in front of the sun maybe once every 15 or 20 days. Okay? So small stars are the most common, but they also are exactly what we're looking for. It makes it a lot easier to study the atmosphere because the signal is bigger and it's more frequent. If I draw a bubble, if I were to go out in space and draw a giant bubble just around the nearby stars, so let's go out to say about 30 light years, okay? And I count up all the stars in that bubble, then here's what you get, okay? So there are no O stars, no B stars. These are the really, really massive stars. There's a small number of A and F stars, and there's about 20 sun-like stars, what astronomers call G stars. So out to 30 light years, we're talking about 20 G-type stars. In that same volume of space, how many of these red dwarf stars are there? Okay? There's 246. Okay? So in the same amount of space where you have 20 of these sun-like stars, you've got 246 of these M dwarfs. So they outnumber us 12-1. So if you're interested in life on other planets, red dwarf stars are great because it's easier to find that life. But they're also great because they just outnumber us 12-1. I mean, if planets form around those kinds of stars the same way they form around sun-like stars, it's kind of inevitable that the closest one to us is going to be around an M dwarf, just because they're so common, these little red dwarf stars. So with that idea in mind, I set out a number of years ago now, about 9 years, to build a special project called the MERTH Project, which was going to focus on finding planets that are small like the Earth and going in front of the very closest small red dwarf stars. So because we were trying to find Earth-like planets in front of M-type stars, we called it the MERTH Project. And here is what we came up with. The idea was we didn't need very big telescopes because the stars were very nearby, but we needed a lot of telescopes because the stars were all over the sky. So we had a list of the very closest few thousand stars, but one was over here, one was over here, one was over here. So we needed different telescopes to look at them all at the same time. We couldn't get by with one big telescope. We wanted to see stars in both the northern hemisphere and the southern hemisphere. And so in the north, we're located in Arizona. And then much more recently, just about 2.5 years ago, we began operating in Chile. Okay? And that gives us access to both the northern hemisphere and the southern hemisphere. And every night, these telescopes go about their business. They are frantically surveying all the nearby stars. And I want to show you what that looks like. And again, if we could just, Tom, if we could just bring down the light a little bit, please, for the next image. Okay. So here's a time lapse of the observatory in action. So you can see all these different telescopes as the stars scroll overhead. But this particular telescope, I'm plotting its data, and it's studying one star, and nothing much is happening until it gets this observation right here. Boom. It's low. The telescope realizes that in real time, and it changes the way it was gathering data. It notices the star is fainter than it had been earlier in the evening, and so it follows that star until it notices that it brightens up again, and then it goes back to its survey observations. This is great for family life. It's fully robotic. I'm home with the kids. I'm making dinner. And lo and behold, of course, then we find out the next morning that Mirth has found a planet. Okay, so that's what that signal looks like. It's blocking only a few parts in 1,000 of the light from the star, but that's our first hint that there is this rocky world. Okay, and this discovery was led by Zach, who I just mentioned earlier in the talk. Okay, so that was a discovery of a nearby rocky world. And then more recently, just recently, we found the one that we're really looking for. So that's what I want to tell you about. So in September of 2014, our observatory, Mirth, found a dip of one of the stars that we've been surveying. So it was this anonymous star. It's got this catalog name, LHS 1140. So even though it's a very nearby star, it's just got this completely anonymous name. But we didn't really think very much of it. Okay? And then a student, Jason Dittman, went back and reanalyzed the data using a very clever software that he wrote, a machine learning software, if you're into that kind of thing. And he found that those data were persuasive. He thought we should go and try to do some follow-up. So we began to do Doppler monitoring. So instead of waiting for another transit to occur, we thought, well, if the planet's actually out in the habitable zone, we're not going to see another eclipse. We're just going to see one. Those are pretty rare. So instead, what Jason had us doing was to actually start to measure the wobble of the star. And sure enough, the star wobbled. Okay? And it took about 25 days to complete its wobble. And then based on that wobble, we were able to predict when the other eclipses would occur. You can see that it took about 2 years for us to sort that out. And then we measured them. September 1st, September 25th, October 20th. Based on the wobble of the star, we were able to figure out how heavy the planet was. And we measured the mass, and it's about 6 times the mass of the Earth. The period of the planet, though, was very long compared to most of the other planets that we've been studying. The planet takes about 25 days to go around its star. Remember what I told you earlier. That means that for this red dwarf star, it's nice and cool. It's not too hot. And in fact, at 25 days, it is probably the same temperature as the Earth. Okay? So it gets about half the light from its star that the Earth gets from the sun. Not 20 or 30 times, not 100 times the way so many planets do, super hot planets. This one was actually nice and cool. And importantly, of course, because we had the transit, we could measure the size of the planet. So we measured the size to be about 40% larger than the Earth. And so it looked like we truly had what we've been looking for, was a planet that had the right temperature, but was definitely rocky. Okay? It was bigger than the Earth. Okay? It was not 1 times the Earth's mass. It was 6 times the Earth's mass. So it was a super Earth, but a rocky world around this star, LHS 1140. And we announced that in April. So just this discovery finally came together and we published it very, very recently. So if I'd been here last year, wouldn't have been able to tell you anything about this. Okay, so what's so exciting is how quickly this field is moving. So if I had given this talk a year ago, I would have said, if we could find such planets, Then we will use the James Webb Space Telescope and the Giant Magellan Telescope to study their atmospheres. But I don't have to say the if anymore. Now I can say, we have found those planets. We hope to find even better ones, closer ones, but we have found the first targets for these kinds of studies. The one I just told you about, that's the one that I got to be part of, LHS 1140. But of course, I'm sure you've heard about TRAPPIST. Same idea, right? TRAPPIST is a small, nearby red dwarf star, but it doesn't have just one planet. It's got 7 of them, okay? Roughly the same distance from us as LHS 1140. Now, all the systems are different in their own way. I would say 1140, what's special about that is we know the mass of the planets. We know that the planet is definitely rocky, a real requirement for life. But it's only one planet as far as we know, although we hope others will be found. TRAPPIST-1, there are 7 worlds, which means we've got kind of 7 chances to go and study their atmospheres. But actually, it's very hard to get the masses for TRAPPIST-1, so we don't truly know yet that they're rocky. Time will tell. And then Proxima. So about 9 months ago, Proxima was announced to have a planet as well in the habitable zone. Proxima is the very closest star to us, but it doesn't transit. So we can't quite use the methods I've been talking about, but now we have 3 nearby stars, all very close to us, that have what we think are potentially habitable worlds. So a really fundamental change from even 12 months ago. Okay, so how are we going to put this all together? So I think what I want to emphasize is the complementarity of these 2 great observatories. Okay? So if we just use the Giant Magellan Telescope, or if we just used the James Webb Space Telescope, I don't think, no matter how good the data was, I don't think we'd be able to conclude that there was life on one of these planets. Okay? And here's why. What we want to do with the GMT is we want to go and detect oxygen. It studies the right wavelengths of light so that we can actually detect molecular oxygen, which is the kind of the giveaway that there's life, right? Life, photosynthetic life makes oxygen. The oxygen accumulates in the atmosphere. The oxygen is entirely due to life on the Earth, and so that would tell us that there really was life on the planet. However, if all we have is oxygen, that doesn't work, because, of course, astronomers have been thinking about this problem, and they said, well, you know, on the Earth, the oxygen is all made by life, but they can concoct schemes where on other planets, the oxygen would not be due to life. The oxygen would be due to, for example, ultraviolet light from the star hitting water and breaking the water up into its hydrogen and its oxygen, and maybe that's how you make oxygen. So if you just saw oxygen, you could be fooled. That's why you need the James Webb Space Telescope. What James Webb can do is it can detect all sorts of other molecules that will distinguish between those 2 scenarios, whether the oxygen is made by life or whether the oxygen is made by some geologic or photolysis process. So putting them both together, I think we actually can go and interpret the data correctly. So perhaps they can do it together. GMT is able to detect molecular oxygen. James Webb really can't do that because of the wavelengths. It just doesn't study the right wavelengths to do that. But by the same token, GMT can't gather the ancillary information that will really allow us to interpret the oxygen detection. James Webb Space Telescope is going to be awesome at doing that. It's got infrared sensitivity. It can detect water, carbon dioxide, carbon monoxide, methane, all the things that put that oxygen in perspective. Okay, so you know, big picture, I really think that that's our first opportunity to go and find life on other planets. With these new observatories, I think we really have a shot at this. It's the first time humanity's been able to make that claim. I might be wrong. There might be lots of reasons why there's no life around planets orbiting M dwarfs. I'm happy to talk about that. But it's the first time we can take a shot at this thing. The point I want to leave you with is that the impact really will extend well beyond astronomy and I think even science. I think when I talk to people, I think knowing whether or not we're it, whether there's other inhabited worlds, and what that relationship of life is relative to life on the Earth, I think speaks very deeply to people beyond just the astronomical questions that it will answer. So in preparing a public talk about a year ago, I wrote some of my students, and I said, you know, I'm trying to convey the importance of telescopes for this work. You know, I said, like, for me, a telescope is like that spaceship. It allows me to kind of go to other worlds, see the local conditions, discover life. But of course, without having to overcome this technological miracle of actually traveling to other stars. I can just go there kind of with my telescopes. What do these giant telescopes mean to you? And so my students wrote back, and I just wanted to share one quote. This is from Hannah Diamond Lowe. Hannah was in the first year of her PhD working with me. And I loved what she wrote. She said, "Spending time at one of the biggest telescopes in the world has given me a grand perspective on the accomplishments of humanity. From this vantage point, detecting signs of extraterrestrial life seems well within our reach." So I love the fact that, for me, this just all seems like this incredible opportunity that I would have never foreseen when I was doing my PhD, which was about, 15, 20 years ago. For Hannah, it seems like it's really something that's on the table. We could really go and actually make these discoveries. And that's a picture of Hannah in front of the Magellan Observatory where she was gathering data. And Hannah is here at the conference, and she's giving a scientific presentation on her results tomorrow. But we haven't discovered life yet, just so you know. Okay, I want to thank the funding agencies that really have made this all possible. It's a really nice collaboration between the federal funding agencies and the private foundations, the National Science Foundation, NASA, the David and Lucille Packard Foundation, and the John Templeton Foundation. And then most importantly, these folks who do all the work: Zach Berta-Thompson, Jason Dittman, Courtney Dressing, Raphael Haywood, Jonathan Irwin, Mercedes Lopez-Morales, Elizabeth Newton, Joey Rodriguez, and Jennifer Winters. I've showed you all of their results, all put together in this picture of the progress that we're trying to make on this big question. Okay, so this is my final slide, but I want to make sure that when in the morning you're talking to family, friends, you wake up and tweet or whatever, this is what you should be talking about, okay? All right, these are the real takeaways that you've got to go home with. 1, red dwarf stars are the most common star in the galaxy, and there's at least one habitable planet for every 4 of them. Okay? A fundamental advance in our understanding that is hot off the presses. That result is only a couple years old. Okay? 2, we have begun to find the closest transiting Earths. Okay? Those results are only a couple months old. And we are planning to study their atmospheres with the next generation of powerful telescopes. And then finally, the search for atmospheric biomarkers such as oxygen, I think, really is humanity's first attempt to answer this great question of whether or not we're alone. And that's the end of my talk. Thank you.
Okay, I'm sure there are plenty of questions because there are always questions when you talk to exoplanets. So, in the center, sir.
If you looked at Earth's atmosphere during times of extreme climates such as the Ice Age, would Earth have appeared habitable? Because it strikes me you're looking at these planets at a very narrow time in their existence, and that doesn't tell you what the future may have held for them.
Yeah, that's a great question.
I have to repeat the question for the web audience.
You should repeat that great question.
It's a requirement of my job. It's sort of like the computer on Star Trek. I have to repeat everything you said. So the question is, if we looked at Earth during the Ice Age, would we see any evidence of life? Because as we've seen on Earth, it can go through very strong differentials in what it looks like.
Yeah, so that's right. So during the Ice Age, the recent Ice Ages, so the recent Ice Ages are tens of thousands of years ago. The oxygen content of the Earth's atmosphere didn't change significantly. There was still plenty of oxygen, which is the signal we're trying to measure. But to broaden your point a little bit, the Earth has definitely changed over 4.5 billion years. When it started out, it took billions of years for the oxygen to build up to the point where it was something astronomers could ever detect remotely. Okay, so for a very long time, even after there was photosynthetic bacteria, They were making oxygen, but the oxygen was probably going and reacting chemically with exposed rock on the surface, for example. So that's right. So what I'm talking about is trying to find evidence for life as the Earth has appeared for roughly the past half of its existence, but not for all 4.5 billion years. I would love to come up with an idea with a tool that was even a broader net and allow me to look for life that would take me all the way back to when life first appeared on the Earth. But I don't know how to measure that from afar yet. So this is what I've got to present as a tool.
Yes or no?
Over here. For planets going orbiting red dwarfs, would a magnetic field be as important as it would around the larger star, our sun?
So the question is, for planets orbiting a red dwarf, would the magnetic field be as important as it might be for a larger star like the sun?
Yes. Do you mean the magnetic field of the star or of the planet?
Planet, protecting it from...
Yes. So a big question is, since these planets are in close to their stars, can they hold on to their atmospheres? If the star has a strong stellar wind, for example, would it simply remove the atmosphere of the planet and then obviously they're going to be habitable? So yes, I think that it is a requirement that the planets, to be habitable, have a coherent magnetic field. If we look at our own solar system, Mars probably lost its atmosphere because it's cooled all the way through, so it no longer has a molten core. That means it doesn't have this coherent magnetic field, and over time the solar wind was able to strip away the atmosphere of Mars. It also was lower surface gravity, so it's easier to let that gas go. Out of interest, for the planet that I was talking about, LHS 1140, it's more massive than the Earth. So almost certainly its core has not solidified, so it's got a better chance of keeping magnetic field, and also the stronger surface gravity would allow it to protect its atmosphere just through gravitational effects as well.
Was there a question in the back over there?
I just had a question about, you mentioned that in 2001 there was one exoplanet known. Now we know of considerably more.
One transiting planet, yeah.
Do you envision that exponential growth and understanding to continue about this in this field?
All right, so we've got a large growth in the number of transiting exoplanets in the past 2 decades. How long is that going to continue? Is it going to keep going exponentially?
Yeah, so I'd like to, the way you said the question was, do I anticipate the same exponential growth and understanding? And I would say I don't expect the same exponential growth in number, but in understanding, I do. So what yielded most of these planets, most of these 5,000, they come from one NASA mission, the Kepler mission, okay? There are other missions coming up, which I didn't even have a chance to cover because there's so many things going on in exoplanets. The NASA TESS mission should launch in spring of next year. We expect that to find hundreds or maybe 1,000 planets. And then there's a European mission called Plato. That should also find, of order thousands of planets. So we will continue to increase the numbers, but it's not going to be exponential. Okay, the way that Kepler really took us from kind of hundreds to 5,000. But the point is we're finding planets that are closer, so our understanding, I don't think we need a lot more planets to do, we'd love to have them, but I think now the issue is moving from statistics to actually a detailed understanding of the properties and compositions by finding the nearby examples of the planets that Kepler told us must be there.
Okay, I saw Cal down in front.
Are we restricting our view based on the fact that we're finding life under very extreme conditions right here on planet Earth?
So I guess you're mentioning that we found life under very extreme conditions on planet Earth.
I'm saying that
how wide of a parameter space do we need to search?
what we're looking at.
Yeah, are we being too narrow and kind of closed-minded? And I am happy to say that yes, I am narrow and closed-minded in my search because I can only search for things that I know how to recognize. Okay, so I think what we've done is we've come up with a plan where we can say, okay, oxygen and the combination of other molecules on a planet that has a certain temperature, I would be able to really conclude that that is due to life. But you're right, there could be life that is more like what we call extremophiles here on the Earth. There certainly is lots of life that doesn't make oxygen. And of course we can imagine other kinds of life that doesn't exist on the Earth but maybe would work chemically. And yeah, I think we would easily miss that. So what I'm presenting here is an idea to recognize life that's pretty similar to what we find on the Earth. It's certainly life that's been around for billions of years on the Earth. Because I have the ground truth of the Earth, I would know how to recognize it. And I hope that kind of my students are going to come up with even broader tests to broaden that net and think of ways to find life that we can't currently figure out how to recognize. But I don't know how to do that, so I'm going to go with the oxygen case for now.
Okay, so there.
Are there any atmospheric markers that are created only by living organisms?
Are there any atmospheric markers that are only created by living organisms?
CFCs, you know, all the pollutants that we produce. There are definitely a lot. I mean, I would say, you know, certain kinds of industrial pollutants and things like that. I think that any interesting biomarker like oxygen is, you know, you can imagine it being naturally occurring. So, you know, methane on the Earth is a biomarker. Methane in the Earth's atmosphere, if you just said, if there wasn't life, and I just did a chemical calculation, how much methane should there be in the Earth's atmosphere? And the answer is there should be less than 1 molecule of methane in the entire Earth's atmosphere. So the methane on the Earth is produced by agriculture, by rice farming, by ruminants, by cows, okay? So that's another kind of biomarker. It's a very trace gas. It's much less abundant than oxygen. So I would say that, yes, I can think of those gases, but all the ones that I can think about that are actually detectable astronomically, like very large quantities, things I know how to go out and measure, they all are pretty simple molecules that certainly could be produced. And so it's always a question of context. The temperature of the planet or the other gases on the planet that allow you to make a decision about what's the provenance of that molecule.
Peter.
Yeah, for those that are looking for life within the solar system, they are looking not at the planets, but at moons of planets like Europa. Now, is there any chance you'd be able to detect moons around some of these exoplanets?
So the question is, would you be able to detect moons around giant planets around other stars?
That might have life.
That might have life, yes.
Yeah, so in the solar system, the reason we look to moons is because we need planets that have the right temperature. And the way the Earth, of course, maintains its temperature is by radiation from the sun, but another way to heat your planet is to have it orbit a gas giant and to be tidally stretched, and that stretching, that pulling, the friction heats the planet. And so, for example, there are planets of Saturn, there are moons of Saturn and Jupiter that are much warmer than they should be due to that tidal energy. So yes, there is a very healthy interest in finding moons orbiting exoplanets, and people have worked very hard on this idea, and nobody's found a single one. Nobody's ever found a moon around a planet orbiting another star. I think this new planet that we just found, LHS 1140, that would be a good candidate for a moon, so we're going to go hunting, but we haven't gotten the data yet. People are searching through the Kepler data, haven't been able to find anything, but there's always a hope that they can improve that. You know, we're not going to get more Kepler data from the original mission, but we can improve the quality of the data by smarter data analysis. So there's a lot of activity, but so far nothing.
Okay, down front here.
You're right that you have to wait for the second half of Earth's history to get oxygen in the air, but the thing you're really looking for is water. And can you detect water in the atmosphere of a planet? Because that will tell you that there's water on the planet, and you need that.
Can you detect water in the atmosphere of a distant planet?
Yeah, great question. So the question was, you know, oxygen is a fairly recent phenomenon, meaning half of the Earth's history, maybe a little bit less. Water has always been around. So yes, I'm proud to say we're really good at detecting water. Water has a big signature for astronomers. It blocks a lot of light. In fact, it's a terrible pain in the neck when you do astronomy from the ground. You have to look up through the Earth's atmosphere, and there's all these parts of the Earth's atmosphere that are blocked by water in infrared wavelengths. So when you're out in space, you don't have to worry about that, and you're looking at other planets. So yes, water has been detected on many, many planets orbiting other stars. Not yet down for rocky planets, because that's much more challenging, and that's, I think, one of the first things that people are going to try to do with the James Webb Space Telescope.
Okay, over here. I always have a bias towards this.
So we'll check over here.
So what do you think are the chances of finding life in our solar system on a moon like Europa?
So what do you think are the chances of finding life inside our solar system on a moon like Europa?
So I really, I often get asked, what do you think? And what if you had to bet? And I really am open-minded. I truly don't know if the answer is going to be there is life outside the solar system or in it or not. So there really could be life on Europa or Enceladus, which is a moon of Saturn, where people are getting excited about looking. I think we have to go. I think the only way to answer it is you got to go. And I think we have to send probes out to those bodies to do a lot of interesting planetary science and also to actually go and look for life. I hope that's not a deeply unsatisfying answer to you, but that's honestly how I feel. I really think that we could find we are truly alone to the best of our ability to study. Or we could find out that the moment we can finally get to another planet or moon, whether it's in the solar system or out, that kind of remotely had the right temperature and chemistry, we're going to find life, and life is this kind of inevitable outcome of having things at roughly the right temperature. We shall see. We've never done the experiment.
All right, in the center in the green shirt.
Two quick things. Number one, the Giant Magellan Telescope, will it be an ultraviolet telescope?
The Giant Magellan Telescope, will that be an ultraviolet observer?
No, unfortunately it won't. To look at ultraviolet wavelengths, you really have to go to space. Fortunately for us, ultraviolet radiation is mostly blocked by our atmosphere, and so you have to get above it to look at UV light. And so really the preeminent observatory for ultraviolet observations is the Hubble Space Telescope.
Yeah, so GMT really can't. It can look at very blue light, but not what I would call ultraviolet.
So what wavelengths are associated with finding the biomarker?
Oh, yeah.
Which are the best wavelengths for finding these biomarkers?
Yeah, so oxygen has a very strong spectroscopic feature in kind of the red optical. At a wavelength of light that's very favorable, and in fact, when you look up through the Earth's atmosphere, it's very prominent, and there's a trick actually how you study it with the GMT. You actually have to get so much light that you can do it at a very high resolution, and the lines that are due to oxygen move out of phase with the lines that are due to the alien oxygen because of the relative speed of that star and us. So the oxygen is something you would do in visible light with a ground-based telescope, but things like water, methane, carbon dioxide, carbon monoxide, those are mostly, maybe with one exception, those are mostly things that all be done from space with JWST.
All right, so we have a question from the internet. When you study a star system, how do you know how old it is? Do you have a good way of estimating the ages of these stars?
Yeah, great question. Do we have a good way of estimating the ages of stars? So for M dwarf stars, for these red dwarf stars, we didn't until recently. So they basically, once they form, they do not show their age. So if you meet a red dwarf star, you can't tell if it is 1 billion years old or if it is 12 billion years old. And in fact, many of them will continue to live long into the future. So some red dwarf stars will live for hundreds of billions of years. They have very little hydrogen in their core, but they burn it. They burn it so slowly that they really don't change. Of course, for the sun, it changes because it's eating up its hydrogen, right? But we do have a way to get their ages now, which is that we've learned that over time the stars spin down. And one thing that I'm very proud of data coming from the Mirth Observatory was we were able to get rotation periods, how these spin periods for these various red dwarf stars. And we think that that's a proxy for age, and so we can tell which among them are the older stars and which are the younger stars. And that was work led by another PhD student, Elizabeth Newton. There's another way to get the ages of stars, and that's astroseismology. So if you have really good data, stars actually pulsate. And those are sound waves, and those sound waves go all the way through the star, and they tell you about what's going on in the core of the star, which is something that changes with age. And so astroseismology is a really great way to do it for sun-like stars. But unfortunately, that doesn't really work for these red dwarfs.
All right. Any of the CTY students, because we have some Center for Talented Youth students here. Yes, questions?
Can you extend more on the machine learning model? Like, what kind of type is it? How is it? What was the training data set?
I'll also say the guys on the internet were fascinated with that. The Mirth telescopes and the machine learning to be able to. identify things.
Yeah, okay, great. Yeah, so Jason Dittman was a PhD student working with me, and he had basically, he you know, like, I think one thing I encourage students to do is he just had learned about this on his own, and he'll tell you, he said, I had a hammer, I was looking for a nail. And so he said, I'm going to try this on the Mirth, I was going to try this on the Mirth data. And so he, I think you asked what is the training data set. So it's a very simple machine learning code, okay? But the training data set is that we basically, the Mirth observatory, what's really going on is that we are getting triggers all the time. So there's moments where the telescope thinks, oh, this star is fainter than it was, maybe I have a transit. And so there are thousands of those events in the data, and what he had to do was to find the one or the two, the small number, that were not just triggers because of bad data, like the telescope had warmed up a bit, or the star was a little off from its normal position, so it made the star appear to be fainter, but it wasn't really fainter. From the very small number of events, in particular this one, that was a real effect. And so what he did was to train, he went and took the in-eclipse, the transit data from known planets, like that one that I told you about that Zach had found in a previous planet. And he said, okay, I know that that's actual good transit data. So then he said, what are the characteristics of that data? And he trained it on that good data. Then he set it loose on the uncategorized data, and he pulled out this one transit. Okay. And what he did, and what was really neat is when he brought me the transit, I have to confess, I've got to watch it as a professor. You get kind of overconfident. And I said, and to myself, I'm like, this is not going to work out. But the guy's finishing up his PhD. I'm gonna entertain him. I think I should cut him some slack, and maybe he's right. And he was right. And that really showed me that I should not be too confident in getting too familiar with data sets. So.
All right. One last question from the CTY. Yes.
So has it possibly been considered that life could exist on a comet or an asteroid?
Has it been considered that life could exist on a comet or an asteroid?
Yeah, great question. So I think that in general, astrobiologists would say they don't expect life to be on a comet or an asteroid because we think you have to have liquid water. And the reason is that you need a way for the chemistry of life to proceed, okay? So if you have a gas, the interesting molecules in that gas are too far apart, so you don't have chemical reactions very quickly. If it's a solid, obviously things are locked in the crystal lattice, they can't move around. So that's why we really like liquids for the early chemistry of life. And so on comets and asteroids, we think they don't have that everything is solid. The orbit of comets, of course, is very, very elliptical, and so they do change quite a bit their distance, but they still remain quite solid. So we don't really think so, but gosh, I'd love to be proven wrong about that.
All right, we have a lot of questions there. Irini Lambridis is here to take people across the street. If you would like to observe at the Maryland Space Grant Observatory, she's your Pied Piper to follow. Next month, Courtney McManus will be back to our regular first Tuesday of the month starting next month. Courtney McManus, The View from Mission Control. And please join me in another warm round of applause for David Charbonneau. We'll have to see, because the Great Red Spot observation is in 21 minutes. Juno passes by the Great Red Spot. Is that right? 9:45.